Hello, in this set of notes I'll be discussing polarity of molecules. Generally speaking, what polarity is it's an uneven distribution of electrons within a molecule so that on one side you have a positive charge and on the other side you have a negative charge. And so whenever people use the word pole, they usually mean there's one part of something that's some way and one part of it that's the other way. For instance, on the Earth, we have the North Pole and the South Pole. In this case, with the Earth, it's talking about magnetic poles. All right, so we have North and South, but in polarity, it's talking about electrical poles. There's a positive end and a negative end to some molecules. And so I'm going to talk about that. So basically speaking here, it has to do with the electronegativity values. Electronegativity, if you'll remember from class, I tend to call electron hogginess, which is the tendency of an atom to pull electrons towards itself, all right? And so here you have that definition. And why this is important is because some elements have really high values, like the ones on the top right of the periodic table, and other ones have low values, like those on the bottom left. All right, and the ones with high values tend to pull the electrons towards themselves if they're in a molecule. And lots of times this can end up in a molecule being polar. So if we have an ionic substance, ionic involves the transfer of electrons, and in that case we say that it's always unequal sharing because you'll have the metal which has given up its electron and the non-metal which takes the electron in, and so we have a positive and a negative there, and it always just exists. And so ionic substances are automatically polar because we get one thing. The difference in electronegativity is so high that one thing just transfers its electron completely to the other thing. And so we have this complete polarity here. But there are two other things that can happen. So with covalent bonds, it could be equal sharing or unequal sharing. So this first picture here on the bottom shows a nonpolar covalent bond. And so the blue there represents sort of the distribution of electrons in the structure. And you see that there's an equal distribution in the nonpolar covalent bond. However, if it's a polar covalent bond, more electrons tend to collect around one side than the other side. And you'll see what these symbols here in the picture there on the right mean in a second. But it has to do with the way that the electrons are spread around the molecule. So we use the word dipole it just means something that has two poles and indicates that we have charged ends. And we use these symbols, it's a lowercase delta positive and delta negative to show that these things have a charge associated with them, but it's called a partial charge because it's less than the charge of a single electron. So delta positive and delta negative means just a small positive charge or just a small negative charge. But it's what happens within a covalent molecule that's polar. We also use this symbol, which is called a dipole moment. All right, it points in the direction that electrons are pulled, and that little cross on the end is to show that the other side of it is positive. So we have a couple examples here. You see this HCl. The chlorine is more electronegative than the hydrogen, so it's going to pull electrons towards itself. All right, so the direction that electrons are pulled are toward the chlorine. And the hydrogen ends up being positive in the end because the electrons are pulled away from it. And electrons being negative leaves the hydrogen positive. In a water molecule, which has this bent shape, what we have is the oxygen is more electronegative, and so there is a pull up towards the oxygen, away from the hydrogens, and so on the top of this molecule we end up having negative charge, and on the bottom of the molecule we end up having a positive charge. The hydrogens tend to be positive for water. We also use this term electron density to talk about how dense electrons are or how many electrons there are collected in a certain area. And so if you see this sort of gray-green cloud that has been put up here, the green indicates that there is a higher electron density around the chlorine because more electrons have collected on that side of the molecule. So generally speaking, if something has high electronegativity, it's going to have higher electron density because it's pulling electrons towards itself. So there are two different kinds of polarity. There's bond polarity and there's molecular polarity. And bond polarity is just looking at the electronegativity differences between two different atoms which are joined by a bond. And we have these general ranges for the electronegativity values. 0 to 0.4 is nonpolar covalent, 0.4 to 2.0 is polar covalent, and if it's larger than 2, it's ionic. And so generally speaking, you're required to know these ranges. However, they're a little bit different depending on some different sources that you might look. So just know that if it's really, really low, like 0.1, 0.2, in that range, it's going to be nonpolar covalent, right? If it's a middle range difference in electronegativity, then we're going to have something that's polar covalent. So if it was something like a 1.0 difference in electronegativity between two atoms, it would be polar covalent. However, if you have really, really large differences in electronegativity, like 2.5 or something like that, it's going to be such a big difference that the electron is just transferred and we get an ionic bond formed in that one instead. And so to give you some examples here, for NaCl, Na has an electronegativity of 0.9, Cl has an electronegativity of 3. The difference there is 2.1. There's such a difference in electronegativity that when Na and Cl bond together, they form an ionic bond. The Na transfers its electron to the chlorine. With N and O, though, the difference there is 0.5. 0.5 falls on the polar covalent range. What that means is nitrogen and oxygen, when they bond, they share electrons, but they share it unevenly. The oxygen, having a greater electronegativity, pulls the electrons more towards itself. H2, that's just two hydrogens bonded to one another. Because they're both hydrogen in that bond, they'd have the same electronegativity, which is 2.1. If they're both 2.1, they don't pull the electrons in any direction at all. It's the same electronegativity. That would end up being nonpolar covalent because the electrons are not pulled to one part of the molecule over the other. And so remembering these pictures here, you would see that NaCl would look like an ionic substance, and then we've got the unequal sharing of electrons on NO, and then H2 is even. So that was bond polarity, talking about the difference in electronegativity between two atoms that are involved in a bond. Now I'm going to talk about the molecular polarity. Molecular polarity has to do with the shapes of the molecules, all right? Because you look at the entire molecule altogether, because this weird thing can happen sometimes. So linear, trigonal planar, and tetrahedral can be either polar or nonpolar. The way that this works is if it's symmetrical, as in the case of BF3, which is shown down in the bottom, what can end up happening is it ends up being nonpolar because the fluorines in that picture of BF3 with the yellow atom and the 3 green atoms, the fluorines are more electronegative than boron, so they're pulling electrons towards themselves, but they're pulling all in opposite directions, and they end up canceling out in the end because it's a symmetrical molecule. The tetrahedron with CCl4 over there on the far right, that one is also nonpolar because the chlorines, again, they're all pulling on the electrons, but since it's a symmetrical shape, they're pulling all in opposite directions and it ends up canceling out. The middle picture there with CH3Cl that has 3 hydrogens and a chlorine on it, that one is not symmetrical. The carbon is actually more electronegative than the hydrogens, so it's pulling electrons towards itself. And the chlorine is pulling electrons up towards the top of the molecule. And so that one ends up being polar. So the general rule of thumb is if it's one of these shapes, linear, trigonal planar, or tetrahedral, and it has the same atom all the way around the outside, like the BF3 does, where they're all fluorines on the outside, or the CCl4, where they're all chlorines around the outside, if they're all the same on the outside, it's going to be a symmetrical structure, and it's going to end up being nonpolar. However, if it's asymmetrical, like the CH3Cl, where there's some atom that's different around the outside, we're going to say that there'd be a difference in the pull of electrons in this structure, and then it would end up being polar. Trigonal pyramid bent molecules, there are 2 bents, but both of them follow this. Those always end up being polar because those are always asymmetrical because the electron pairs that exist on them. And so if it's bent or if it's trigonal pyramidal, it is always, always polar. Linear, trigonal planar, and tetrahedral, you have to work out for yourself whether they're symmetrical or not by looking at the atoms that are around the central atom, and that's how that will work. Here, this is an example of a trigonal pyramidal structure. What you see is the hydrogens are all on the bottom. There's an electron pair on the top that we don't see in this structure. And so what's happening is the nitrogen is pulling electrons from the hydrogens up towards the top of the molecule. The hydrogens on the bottom become relatively positive, and that's why we would say the trigonal pyramidal structure there is polar. So there are some applications of polarity that come into play. One of them is that if you have polar molecules, they align with electrical fields, all right, and they're actually deflected by magnetic fields. And so some way that this is shown is if you ever take a comb and you're like combing your hair with it and you put it in a stream of water, you'll see that the stream of water bends toward the comb, all right? That's something that people sometimes interact with. If you used a nonpolar liquid like hexane, it would not be attracted to a charged object in that way because nonpolar substances are not attracted to electrical fields. This is the other thing that I think is actually more important. So polarity determines what substances will dissolve and what other substances. There's this rule that we say like dissolves like. What this means is that polar substances dissolve in polar substances and nonpolar substances dissolve in nonpolar substances, but a polar and a nonpolar substance will not mix with one another. So if one thing is polar and one thing is nonpolar, they will not mix. And so if we look over here at this picture with oil and water on the right, what that's showing is that oil, which is nonpolar, does not mix with water, which is polar. If you think that you had something like sodium chloride, right? Some of you know that sodium chloride would dissolve in water. If you put sodium chloride in oil, it actually does not dissolve. Sometimes I'll be making baked potatoes at home, and I'll take salt and mix it with oil, and then I'll take the potato and I'll roll it in that to get the outside of the potato covered in salt and oil so that when I bake it, the skin is really delicious. And I noticed then that the salt does not mix with the oil. It just sits at the bottom, and so that's a case where that happens. This is also important in things, I like to talk about soap because grease and oils are nonpolar, and so if we didn't use soap in laundry machines or when we washed ourselves, we'd have a lot harder time getting rid of the oil and the grease because when you put water on something that's oily, the water just tends to kind of slide off and not get rid of the oil at all. What soap does is, soap is kind of an interesting molecule. It's actually, soap molecules are really large, and they have a polar component to them, and they have a nonpolar component to them. And so soap has this special tendency that it can mix with oils, and it can mix with waters. And so what it can do is it can take the oils and sort of break them down and help them to mix in with the water so that they can be carried away. So that's why we use like laundry detergent or why we use soap when we clean ourselves, is because it helps to break down the oils and carry them off with the waters because oil doesn't mix with water normally. There are a lot of other applications to polarity which you can look into if you like, but I think it's something that is pretty interesting that comes about because of the difference in these different properties, whether something is polar or nonpolar.